So hello everyone and welcome to the organic part GSI 2022 part 2 solved. So let us check this first question that has been given to us. So as you can see that acid is present, so protonation would happen in the OH and then ring expansion should take place due to carbocation stability. So secondary carbocation would form first, as we can see. So let us see the mechanism. We would know more about this reaction. So as you can see that first OH2 plus is forming, so then H2O leaves and we get a secondary carbocation, and this 2-degree carbocation after that undergoes a ring expansion reaction. So this ring expansion is a rearrangement that is happening to the 3-degree carbocation, the corresponding 3-degree carbocation. Sorry, a 7-membered compound actually formed because this is already a 6-membered cycle. So on ring expansion, this would actually give us a 7-membered cycle. And on drawing the second 7-membered cycle with the proper functionalities, the methyls, we actually see that the positive charge now that has formed is a 3-degree carbocation, which has got more stability than the 2-degree carbocation, and hence the ring expansion happens. That is the driving force of the ring expansion. After that, the chloride attacks corresponding to the carbocation, and we actually get the product. And hence, as we can see, the product here is option number D. So the fourth option is the correct answer. Okay, let's move on to the next question. So we have been asked reactivity in soluble acid conditions using formic acid. So as we can see that OTS is present, which is actually a very good leaving group. So we have to actually check the stability of the carbocation that is forming after the leaving of the OTS group. So let us draw the particular carbocations and check the stability. So for pair X, if we see for pair X, we can see that we have got OMe in one particular benzene ring and NO2 in another particular benzene ring. So OMe is electron donating, and here we can see that there is no plus M effect that is stabilizing the carbocation. Only inductive effect is actually stabilizing the carbocation in both the cases. But the presence of OMe as an electron donating group in the benzene ring actually causes benzene to have a little bit of plus I effect, which actually stabilizes the carbocation a little bit more, whereas NO2 being an electron withdrawing group is completely using the minus I effect on the benzene ring, so minus M effect on benzene ring, and this minus M effect causes the benzene to become much more electron withdrawing, hence the carbocation is not stabilized. So for this case, 1 for pair X, 1 is the most stable. And let us see what happens for pair Y. So for pair Y, we can actually see that we have been given this OTS in a 8-membered ring, which is actually fused with the phenyl ring. So phenyl ring actually has got an electron withdrawing inductive effect minus I, though it has a plus M effect. So it has got, it can donate electrons via resonance or delocalization, but in general it has got a minus I inductive effect, and inductive effect is a field effect. So further the carbocation is forming from the phenyl ring, the more stable it is. So because here the inductive effect is an electron withdrawing one and minus I one. So plus M is not happening here, as we know. Hence carbocation stability depends on the minus I effect. And here I think so as the carbocation is farther from the phenyl group, it is actually more stable. Closer to the phenyl group, it is actually lesser stable because of the presence of minus I effect. So here 4 should be more stable than 3. Hence for pair Y, it should be 4, which should be more reactive in under soluble acid conditions, and for pair X, it should be 1, which should be more stable for soluble acids. So not 3. So I am very sorry for making this mistake. So 3 is not more reactive, it will be 4 is more reactive, and option B should be the correct answer. So please note down here, option B should be the correct answer, and please check yourself too. Thank you. Let us move on to the next question, and I apologize for the mistake that I written mistake that I did in the previous one. So for this next question, we can see that we have to find out the relative order of reactivity for SN1 for the following bromides. Once again, in SN1, carbocation is formed, and then the carbocation actually undergoes a subsequent attack by a nucleophile to form the product. Hence, we can actually say that for this, we also have to check the carbocation stability. If the stability of the carbocation is more, then the reactivity for the SN1 reaction would also be more for the following substrate. So let us see. For the first one, it is actually an allylic carbocation, and after that, in the second one, it is actually cyclopentadienyl cation, and the third one is actually a prenyl cation. So as we can see that for the second one is a cyclopentadienyl cation, I think most of you will know that a cyclopentadienyl anion is actually an aromatic compound, whereas the cyclopentadienyl cation is extremely unstable as it is an anti-aromatic compound. And for the prenyl one, we can actually see that it forms a canonical resonance structure which is actually aromatic in nature, so it is pretty much very stable, and this prenyl group actually forms the aromatic structure. Hence this will actually have the highest reactivity in SN1 because this particular carbocation would be very much stable via aromatic stability. So 14 plus 2 pi electrons and cyclic prenyl group is present, whereas for the primary, for the allylic carbocation that we have, intermediate stability would be present. So hence we can see that the reactivity order would actually be the number 3 would be undergoing the SN1 reaction in the fastest due to having the aromatic stability for the carbocation, and after that it would be 1, then it would be the second one. So this is the answer, C, option C. Okay, let's go to the next question. So in the next question we can see that the compound is actually be reacting via SN2 mechanism. So for SN2, backside attack is actually required, and steady hindrance should be as little as possible for that particular backside attack to take place, and the reaction happens in a concerted pathway. So most suitable substrate for this type of SN2 reaction would be a primary halide, let's say. So let us see an example of how a SN2 reaction using a primary halide would take place with the nucleophile. So as you can see that an intermediate step would be present for the nucleophile and the leaving group, both would be present along with the carbon, which is an intermediate or transition state. So after that we actually get the product, which is the RNU by the leaving of the X. So for the first option we can actually see that there is no backside attack that can take place because it is particularly a phenyl group, and which is quite bulky, and the phenyl cation is also very much unstable. So any positive charge in the phenyl group is very much unstable, hence no SN2 or no substitution reaction can take place in such conditions. For the vinylic cation, it is also very much unstable, and there is also a partial double bond character in between the carbon and the bromine, or in any case for vinylic halides the carbon and the halogen have got a partial double bond character. So here also there is no SN2 that is actually possible. For SN2 you need sp3. And for the third option we can see that bridgehead cation would actually form, so positive charge would concentrate on the bridgehead, so which is a violation of the Brett's rule. And once again for SN2 a backside attack should be possible for the nucleophile. Here the backside is very much statically hindered, hence there is no SN2 possible. So the option D, fourth option, none of the above, is the answer for this particular question. So let us go forward to the next question. Here we have been asked to rank the alkyl bromides from most reactive to least reactive in a solvable lysis reaction using aqueous acetone. So aqueous acetone means it is actually a aprotic solvent, and solvable lysis reaction is happening. So the carbocation stability is once again very much important. So let us first draw the carbocation by omitting the bromine group. Let us think that the bromide has actually left as Br minus, and carbocation plus charge has formed in between the two methyl groups. So as we can see that in the first compound that we have, it actually has got SME, so a thioether group is present, which is actually quite electron donating, just like OMe. So ether group is also quite electron donating, and due to this plus M type of character of the SME, the carbocation is very much stabilized in the case of 1. For NaCO3, which is an amide, it is also an electron donating group, so this also actually can stabilize the carbocation, but it is all the electron pull also happens in the C double bond O present with the amide, hence this is lesser than SME. NO2 is electron withdrawing, so there is no such stabilizing effect, and the alkyl group in the fourth option is plus I effect. The inductive effect happens, which is a weak field effect, but it still stabilizes the carbocation more than 3. So the order of reactivity should actually be 1 should be the most reactive, then there should be 2, then should be 4, and there should be 3. So the answer is the option B. So second option is actually the correct option in this particular question. So let us go to the next question. Let us see the reaction that is happening. So in this case we can see that the H and the bromine are present in opposite directions, and hence OH minus actually attacks the H and the bromide leaves, and we actually get a product which is this particular question where as X. And then we actually see our next compound where we see that the H and the bromide are present in the same direction. So let us rotate the bond to make them in the opposite directions. So we rotate the bond of the carbon containing pH and bromide, and we can see bromide goes in the above direction and pH comes in the below, and we can see that H and B are in anti-periplanar configuration, undergoes the elimination, and we get the Y. So for this question, anti-periplanar configuration is actually required for H and Br to undergo that particular type of elimination. Hence the second option is the correct option. You can also use Sawhorse conformation for the previous question to understand it in a better manner. So let us see this question. So let us draw the chair conformation first for the substrate that has been given to us. So on drawing the chair conformation, you can see the methyl is in the below, and also the isopropyl group is in the below. Chloride is in the above, and H we can see one H is actually in the anti-periplanar, another H is in the equatorial. So OMe minus is the good base, so it will actually take that particular H and cause Cl to leave because that H is actually present in the anti of the Cl, and hence it is going to leave and form a C double bond C at that particular carbon. And then we can see that here, hence what is happening is that the least substituted alkene is becoming the major product, and that is known as the Hofmann product. The Hofmann product is the least substituted alkene is the major product, whereas the Zaitsev product is the most substituted alkene is the major product. So you can remember as Zaitsev, let's say it starts with S or Z. So S means substituted. So more substituted means Zaitsev, least substituted means Hofmann. Okay, so let us check out this question. So we can see that we have been asked to find out which of the following statements are true about E1 reaction of an alkyl halide in presence of base. So E1 depends only on the alkyl halide because it is a unimolecular elimination. So rate is only dependent on the alkyl halide. So as you can see, the first statement is perfectly correct because doubling the concentration of alkyl halide. Second question, concentration of base, it doesn't depend on the concentration of base. So it is wrong statement, second statement. Third statement is completely correct because it decreases by changing the alkyl halide from 3 degree to 1 degree because the 3 degree carbocation is more stable, and in E1 reaction unimolecular first the carbocation forms. So carbocation stability determines also the rate, and the rate of ionic reaction obviously increases by changing solvent from DMSO to CH3OH because CH3OH polar protic solvent and hence helps in stabilizing the carbocation. DMSO being aprotic cannot do that. So as you can see that 1, 3 and 4 are the correct statements, and hence our option C is the correct answer for this question. So let us check out this question. Okay, so we have to find out the EPAC names of the substrates X and Y and in the following reaction. So let us first do the EPAC name. So as we can see that the least priority is in the horizontal direction, and bromide is 1 and the above group is 2, second priority, and third priority is methyl. It is going in clockwise, so it is okay, 1 second. Okay, in the first one is 1, 2, 3. Okay, so no, I'm sorry, the blue ink that I have written 1, 2, 3 should actually be anti-clockwise, so it is actually R. So in the second carbon is actually R configuration, and the first one, as you can see, bromide is 1 and ethyl is third, and the second it is actually S because it is going in the clockwise direction, and the least priority is in the horizontal bond, hence the opposite we are taking. So 1, 2, 3 in the anti-clockwise direction it is giving us R, and in the above one 1, 2, 3 in the clockwise direction is giving us S. Hence it is 2R 3S. So you can check the options. It is 2R 3S. Then the reaction happens with NaI and acetone. So let us write the reaction in Sawhorse configuration, the substrate in Sawhorse configuration. So this is the substrate in Sawhorse configuration. We can write it as such. Now we should move, rotate the bond so that the two bromides are in the anti-periplanar configuration. So let us rotate the bond, and anti is required for this particular reaction to happen. After that, the iodide actually takes the bromide and kicks another bromide out from the molecule, and we get the E alkene. So the E alkene is the product that we obtain in this particular reaction. Hence it is, our answer is I think A. It is X is 2R3S 2,3-dibromopentane and Y is E pent2ene. So hence the option A is the correct option. So as you can see that the E alkene is forming. Okay, so thank you. Let us go to the next question. So this is the last question for this part. We have been asked to find out the major product in the following reaction sequence. Let us see the mechanism. So what can happen is we have been given an ester group. So there are two protons adjacent to the ester group, in the adjacent carbon to the ester group, and these two are acidic protons. MeO minus methoxide being a base abstracts the acidic proton, and the negative charge that is formed is actually also stabilized by the ester. After that, the negative charge opens up the ring, the anhydride ring that is being formed, and we actually get this type of a compound, which in the presence of the acid in the second step, H plus H2O, gives us the product, which is the answer. So the option number 4 is the correct answer in this particular question. Okay, so with this we finish the second part of the organic chemistry, and as I always say, thank you so much for listening to this video. Practice organic chemistry quite well, and subscribe to the channel so you would know when new videos would come, and keep on practicing. Thank you.